Welcome to Performance System Development's Duct Installation and Testing, Benefits of Tight Ducts in Tight Homes. Again, it's part of our 2014 webinar series. I'm Mike Arblaster, coordinator for the Pennsylvania program. This is the fifth in a series of 6 webinars. Our next webinar will be on November 13th. The title for that will be Water Managed Roofs and Walls. Here's an overview of FirstEnergy's program for energy efficient new homes. We're offering a builder incentive of $400 plus 10 cents per kilowatt hour in projected savings over the 2009 ACCA reference home. Eligibility depends on homes located inside of a FirstEnergy utility and a certificate of occupancy that for Ohio is dated after March 23rd, 2011. For Pennsylvania and MedEd, Penelec, and Penn Power, that date goes the whole way back to October 28th, 2009, and in West Penn Power after June 1st of 2013. Homes also need to be 15% more efficient than the 2009 IACC or relevant code when the home was permitted, and that would apply to homes really specific to the MedEd, Penelec, and Penn Power, where we have a date that goes the whole way back to October 28, 2009. And also, as a final requirement, homes need to be ENERGY STAR certified. Overview of this webinar, we're going to go over basic concepts, and by basic concepts I mean those that are relevant to duct leakage. We're going to look at symptoms of leaky ducts, benefits of tight ducts, duct installation for ENERGY STAR version 3, the duct testing requirements, ENERGY STAR version 3 credentialing for HVAC. It's going to be a short slide added to the end of this webinar. And then review again of FirstEnergy incentives, ENERGY STAR marketing resources. So the basic concepts. Let's start with duct leakage requirements. Here's a table that includes what's required by the IRC in 2009-2012, which relate directly to the IAC 2009 and IACC 2012. What we're going to be interested in today is looking at the ENERGY STAR version 3 requirements. And for those, I'm just going to start here with the post-construction leakage to outdoors at less than 4 CFM per 100 square feet of conditioned floor area. Notice the asterisk here. We're going to touch on that later. For ENERGY STAR, whether it's rough in with or without the air handler, the total duct leakage needs to be less than 4. And the final test for total leakage has to be less than 8 CFM. Now, if all of the air handler and ducts are located inside the conditioned space, testing is required by ENERGY STAR. And it's really one of the main points that we were going to get across during this presentation is why is this so important still? Even if all of the ductwork is located inside the envelope, why are we concerned with that? So that's what we're going to move into next. Let's take a look at these two, 4.1 and 4.2, Section 4 duct leakage. Here we have the requirement 4.1, total rater measured leakage, duct leakage of less than 8 CFM per 100 square feet of conditioned floor area, and leakage to outdoors in 4.2 of less than 4. And here's this asterisk that we've mentioned. So there's been a change, and this is effective June 10th, 2014. So any home with a CO date, going back to this date, this is allowable. For a home with a dedicated return in each bedroom, and this is not a bedroom pressure balancing feature leading to a central return. We'll talk about that more later too. But the total duct leakage is permitted to be the following. 1, the greater of 6 CFM per 100 feet of conditioned floor area, or less than 60 CFM at rough in. Or 2, the greater of less than 12 CFM per 100 square feet of conditioned floor area, or less than 120 CFM at final. So this is a significant laxing of the requirement, and we're going to touch on this a few times moving forward, but in no way want to downplay the importance of sealing ducts and what the benefits of having a tight duct system are. So let's keep moving right along. More basic concepts, heat loss and gain. It's going to be important to look at heat loss, gain, equipment sizing, and duct design. all in part of getting to our explanation of the benefits of having the tight ducts. So let's look at heat loss and gain first, see how we're getting to this duct design to begin with. Heat loss and gain is basically something calculated through ACCA's Manual J. It determines the building heat loss and gain characteristics. In short, we can take a look at this building and see that you have heat loss and gain through the ceiling, through walls, windows, doors, and the whole way down to the slab. You also have gains that come from the sun that's calculated through ACCA's Manual J. And then there's the sensible and latent heat gains that come from lighting, appliances, people, and pets. And that in addition to sensible and latent gains that come from envelope infiltration. So any place where you have dissimilar materials meeting, or any place different parts of wall and ceiling assemblies meet with one another, there's a lot of potential for infiltration from the outside. Once you come up with a good load calculation, determine this gain, you're going to move on to equipment sizing. And this is the ACCA Manual S, and it relies on the Manual J calculations to correctly size equipment. Some of the basics of sizing, when you're looking at heating sized from 100% to 140% of the design loads or the next nominal size. In cooling, this is sized from 95 to 115%. There's a 125% limit for heat pumps, or also the next nominal size, which in this case can be in half or full ton increments. 1 ton of cooling is approximately equal to 12,000 BTU hours, so if you were to look at a 2.5 ton air conditioner, that would provide 30,000 BTU hours of cooling. Also, a 1 ton of cooling provides approximately 400 CFM of airflow. So if you have a unit that's a 2.5 ton air conditioner, should be capable in the range of 1,000 CFM. The capacity of an air conditioner, what makes heating kind of very easy to size and what makes air conditioning a little more tricky, and really will be a large part of the focus of our benefits of tight ducts as we move through this webinar. But capacity of air conditioner really is a moving target, and it depends on naturally the outdoor and indoor temperatures, but it also significantly impacted by the indoor humidity. And another variable that's system dependent is the airflow that is moving across the indoor evaporator coil. And we're going to talk about that in a little bit more detail as we move forward too. I mean, the main point is that in equipment sizing, might is not always right. Oversized systems have higher initial costs. I mean, many contractors charge by the ton, so going to a larger system is more money in the contractor's pocket. Oversizing systems reduces efficiency, especially in warm, humid climates where oversized equipment short cycles, and it results in reduced extraction of latent heat. Short cycling system is not going to adequately dehumidify inside the house. Along with this, come higher, increased energy costs, and the constant starting and stopping of the system can cause, excessive use. And then there's the compromised occupant comfort. Occupants need to endure a system that will flash heat or flash cool the living space. And an example, in a humid home that's being flash cooled, you have occupants that feel the immediate relief, similar to walking into a cool basement. It feels great when you first walk in there, but if you spend too much time, you start to get a sense of this clammy, cool air, and that's not really what we want in terms of comfort. In addition to going too big on the system, it shortens the overall life, and this is reduced to the system's ability to properly saturate the refrigerant, which ultimately can result in more of a liquid refrigerant entering into the compressor, which will burn up an air conditioner compressor, and we'll hopefully discuss that in a little bit more detail, but not too much. And next we move on to duct design, some of the basics here. This is ACCA Manual D. It provides guidance for proper air distribution. And ideally, what does an ideal system want to include, and as opposed to going through, design and distribution process. I mean, ideally, what we're looking for is a system that's pressure neutral, meaning that you have supply air that's equal to return air in the system. Ideal systems are not exposed to unconditioned spaces. The ideal system supply and return air are from the designed locations. So we don't have a leaky return inside the conditioned basement that weakens the strength of the returns in upstairs bedrooms. We want to be able to return the correct amount of air and supply the correct amount of air from the desired locations. So ideal duct systems are not leaky, and ideally building cavities are not used as ducts. So I'm just going to move right along. So what are some of the symptoms of leaky ducts? Well, here's an idea of what we're going to be getting at, and this is important how you're going to talk to customers about these things. So all of the things that we're talking about here end up costing money. The first two are pretty easy, and then let's think the next two are might have to use your imagination or just science. But symptoms are higher utility bills. Like why are they have the utility bills increase? And the short cycling equipment. This is going to cost money. I mean, if you fail a compressor or the system goes down, you have to pay to replace it. And then here's something that is a really good thing to look at when you're thinking about duct systems is think maybe a little bit less about overall airflow and really consider the pressures, because that's what's important. Pressure in the ducts and the pressures that can be created. So these are unwanted house pressures that can be created by leaky ducts, leading to uncontrolled infiltration and exfiltration. We'll hit on a few examples of that later, and ultimately poor air quality. So use your imagination a little bit here, but we'll touch on how these leaky ducts can result in reduced air quality. So here's a really important slide, and this is the one that's going to take a few minutes to get through, and hopefully we'll speed up on some of the slides later. But we're going to talk about airflow here at the coil, and there's a bunch of different ways to look at this, but this is the basic refrigeration cycle. Look at this where an evaporator is designed for a very specific airflow, and the reason for that is what makes this process work, what allows the refrigeration process to work. So an incorrect airflow coming across the inside evaporator coil. Here's indoors, here's outdoors. I'm going to create a little analogy later to help remember this and explain it to customers. It seems to work for me. But when you have the correct amount of airflow here, you get the absolute maximum amount of heat removal, because those BTUs enter this liquid refrigerant, flash it into what exits the coil as what is a low, still relatively low temperature. It's still, it's filled with BTUs, but it's a low temperature, low pressure gas. And it enters into the compressor where that vapor is transformed into a high pressure and then high temperature gas. It enters the outside condensing coil, and which rapidly evacuates the BTUs to outdoors. And if you ever held your hand over an outside air conditioner, that is the rapid evacuation of the heat. You can feel the heat being evacuated. And what happens through this process is they call it a condenser, because that vapor is transformed back into a liquid, and it's a high, still relatively high temperature, high pressure liquid, and then it enters into the expansion valve, or usually a TXV. But at that point, the pressure is released. It turns into a low pressure, and with the pressure dropping, the temperature drops, and so you return now to a low pressure, low temperature liquid that again enters into the evaporator and rapidly absorbs BTUs, flashing it back into a gas, and this process continues. Overly sized equipment will not properly manage humidity, in addition to not getting the correct amount of vapor in the vapor line. In this, when you have a short cycling system, and the point that I was hoping to get to here is that damages can be caused from this, and this is in addition to excessive starting and stopping, which uses more power. Not having correct airflow can be exacerbated by ECM motors too, that will work much harder to try to get the correct amount of airflow to move across this coil, ultimately controlled by the subcooling and superheat, which, just to mention briefly, is the temperature by which this has exceeded transforming into a gas, and then again, when it comes through the TXV, it's transformed, or coming out of your condenser when you're transforming back into a liquid. You want to get a certain amount of subcooling to the refrigerant. So here's how this can result in some equipment failures, and I'll give you a little example here. But you don't want to compress liquid in the compressor. It's designed to compress vapor. And when this refrigerant is flashed into a gas, it takes on X amount of degrees beyond what it took from saturation temperature, where this is a perfect mix of half gas, half liquid inside here. When it comes out this end, it needs to be all gas and a superheated gas to X amount of degrees, so that when it arrives at the compressor, it is compressing a gas, and there's no liquid coming into here. And if you ever heard liquid entering into a compressor, you'll know, because it makes a different sound. You can hear the strain, you can hear them whine, and sometimes if you see the thing really rock itself into place, you'll know that it's getting some liquid in the compressor, and you don't want that. Additional strain on these systems come from the starting and stopping of the fans, the compressor itself, and when you have leaky duct systems and you're drawing, they're not adequately dehumidifying or creating negative pressures that can increase the humidity. You can overuse the condensate pump. Just to summarize on this slide, and then we'll move right along. One of the things I like to imagine when I think about this cycle is that there's sort of like a locomotive that is going around this little set of train tracks here. Maybe we got a Christmas tree in the middle, but the train kind of comes into the station, and it's got a bunch of train cars that are able to be filled with BTUs. When the correct amount of airflow is moving across this coil, you get the maximum amount of train cars that this system can handle. So this train set gets the maximum amount of train cars by having the proper amount of airflow that can dump the best, highest, most efficient amount of BTUs into that train, that then takes all the BTUs outside, gets put into some kind of state that it can be evacuated, but basically all those BTUs are then evacuated here at the condenser outside, and the empty train comes back in and gets filled up with BTUs all over again. And if you don't have the right amount of airflow, then you're reducing the number of train cars that are able to be added, and reducing the efficiency of the unit. Let's look at unwanted house pressures. And this is what we wanted to get into next, and look at some of what can happen here. Unwanted house pressures, especially leaky return in conditioned basement, for instance. This is an example of what a house would look like just under regular stack effect. You have positive pressure at the top of the building and negative pressure at the bottom. Well, if you were to add to this a very leaky return in the basement that's further drawing in negative pressures from outside, then what you ultimately will do is create additional negative pressure in the basement, which exacerbates the idea that you already are creating a negative pressure there. In addition to that, it reduces available return air from the design locations. So if all of the return air is being drawn from the basement, creating a negative pressure here, upstairs returns are going to be weaker. So if you're dumping 150 CFM of supply air in, you're supposed to be returning 150 from each room. This puts you in a situation where maybe you are only drawing 100 CFM out, and therefore over-pressurizing the bedrooms, and even from the top, adding to the positive pressures of the stack effect. Leaky return in conditioned basement creates unwanted negative pressure in the basement, and this leads to the infiltration of moisture. The equipment needs to run more to manage the humidity because you're drawing in all that moisture and sending it across the air handler. And if the system is oversized, problems are compounded, and we discussed that, especially in terms of short cycling line energy efficiency, and again, damage potentially to the equipment. And this also extends into poor air quality. So we can look at leaky ducts and air quality by saying, okay, if you have a negative pressure in the basement that's not only drawing in the humid air, but the humid air then is distributed into the supply runs. So you're pushing humid air throughout the house, and ultimately the humid air is not adequately returned due to the leaky ducts. So you bring in extra humidity, try to condition that air at the air handler, but end up pushing humid air into the remainder of the house. And then you're trying with a weak supply or weak return run because you have leaky return in the basement. You're not getting the right amount of return air, so you're leaving upstairs rooms filled with air that should be conditioned and possibly filled with humidity. Just to go back, I mean, this type of a scenario is something that directly competes with what we're trying to do with our mechanical ventilation systems. And just to look at that briefly, I mean, why we have the ventilation is, one, to have fresh air for our occupants to breathe, and second, to dilute air pollutants and excess moisture. And I mean, what we're doing by not having a balanced system, you can look at this house and imagine high positive pressure at the top, and a pressure difference that's going to influence some air movement. That means that the moisture, anything, moisture, mildew, all of that is going to be then drawn in by this negative pressure, and therefore contribute to diminished indoor air quality. Properly sealed ducts and adequate ventilation. This is what we're looking for. These things reduce the introduction of natural pollutants because we're taking control of the pressures inside the home. So if there are the regular introduction of these normal radon gas, oil leaking to the surface, carbon dioxide, ammonia, these things, pollen spores, natural pollutants, by not creating these additional negative, unwanted, uncontrolled pressures in the home, we're limiting the amount of this. We're also helping to control the indoor pollutants by getting the correct amount of air delivered back to the air handler for conditioning. So we want to return as much as we can back to the filter from dusts and bacteria. And additionally, we want to be able to best dilute gases, the carbon monoxide, of course, by introducing fresh air. We don't want to create scenarios where our fresh air is being further infiltrated upon or creating positive pressures that's evacuating our fresh air out of the building where we don't intend it. And also, of course, this helps control humidity, which is reducing some of the latent heat gains and creating a more comfortable and ultimately healthy living environment for the occupants. So to summarize here on the benefits of tight duct systems, it's everything that we're avoiding in our symptoms. So let's take a look at them, and just to summarize, and these are a good way of talking to customers and even some of your builders about how they can talk to customers about benefits of tight duct systems. The equipment's going to run more efficiently and last longer. So all these things that we talked about before that cost money, this is how they save money. You have a more efficient system that's going to last longer. Occupants have to deliver the right amount of conditioned air to the right places. The system's balanced, which reduces the potential for unwanted positive or negative pressures in building cavities or entire rooms or any other part of the home. And you take control over the unwanted pressures. This reduces the potential for the infiltration of unwanted contaminants and pollutants. So now, this next couple sections are going to move along a little more quickly, and I feel like we're doing pretty good on time, so I'm just going to continue moving along about halfway through. So here's duct installation quality, and this is from Energy Star, and we're just going to go through section 2 for duct quality installation, and then we're going to move into talk about duct testing, and again mention the requirement laxing for homes with dedicated returns for bedrooms. 2.1 is that connections and routing of ductwork should be completed without kinks or sharp bends. We all get it. We don't want excessively coiled or looped flex duct. Flexible ducts in unconditioned space, not installed in cavities, smaller than outer duct diameter in conditioned space, not installed in cavities, smaller than the inner duct diameter, or just don't use cavities as ducts. Flexible ducts supported at intervals as recommended by the manufacturer, but a distance of less than 5 feet. A couple more here. Like I said, the best summary here is don't use real ducts. The main point is building cavities shouldn't be used as ducts or returns unless they meet these certain criteria, the checklist. But the better idea is to just not use them. HVAC ducts, cavities use ducts in combustion inlets and outlets may pass perpendicularly through exterior walls, but shall not be run within exterior walls unless there's an R6 continuous insulation. Again, that's something mentioned in the thermal enclosure checklist, but ultimately something that you don't want to do. And moving down in the last two sections, quantity and location of supply and return duct terminals match contractor balancing report. We talked about some of the balancing, and we talked about bedroom pressure balancing. And this is just one way of checking to make sure you're getting the correct amount of supply and return from the bedrooms. The duct testing portion for the Energy Star version 3 goes as follows. We got total leakage of less than 8 CFM per 100 square feet of conditioned floor area. We have leakage to outdoors of less than 4 CFM. And this became not a requirement, but a recommendation for 3 is that duct boots sealed with floor wall sealing using caulk foam, mastic tape. You don't have to do it if you can pass the test, but you're going to pass. You're a better chance of passing if you follow those instructions. So here's these 2 points where there's been, we just talked about those two, but the duct leakage, total rater measured duct leakage of less than 8 CFM per 100 square feet of conditioned floor area, that's the one. And then you have rater measured duct leakage to outdoors, less than 4. So what has changed is this, that if this footnote is going to be added for a home with a dedicated return in each bedroom, i.e. not a bedroom pressure balancing feature leading to a central return, the total rater measured duct leakage is permitted to be 1, the greater of 6 CFM per 100 square feet, so that is a laxing from 4 at rough end, or the greater of less than 12 CFM per 100 square feet of conditioned floor area, 120 CFM, 25 at final. So that is the change. And keep in mind that this is effective as of 6/10/14. So we'll mention this one more time before we wrap up today, but here's just some examples. On the right side here, we got the thumbs up. This is a demonstration of a dedicated high-low returns that going. Here's one for one bedroom on this side. Here's one going to the other bedroom on the other side. And here we see where there definitely are no. Looks like a big piece of panned return, something panned there, but you don't see individual supply and return runs coming out of this. There's maybe one here that someone used some downspout to create, but I had to add that one. So kind of creative. Probably can get a good 35 to 50 CFM through there. And here's another example of where this is not a way of meeting this requirement. You can't use jumper ducts, so there has to be a dedicated return to each bedroom to qualify for the added footnote. This is something just to mention, and it's part of the requirements, not necessarily part of the change, but leakage limits are assessed on a per system rather than a per home basis. And I'm just going to touch on this real briefly. I have a visualization, probably not as good as the train driving around the tracks to get rid of BTUs, but something similar. Previously, the rater would add together the leakage of the two different systems, and as long as they combined met or under the threshold, then it would pass. So this would be an example. If you have a home that's 2,800 square feet, it's split kind of equally, a little bit weighted towards System 2, but you used to be able to get away with this. So if you needed 8% of floor area, it would be divided up this way, where System 1, maybe if this one tested at 54 and 170, we know we need 224 CFM 25 as the total for the conditioned floor area of the home, and this would have passed, and that's not allowed anymore. One way I was just trying to visualize this is, if this guy were 2 duct systems, and you would look at it by saying the total we need for both of these for the home used to be this 224, but you could have, a very leaky system on one side. This would be our 170 CFM of leakage, and if this guy was sort of divided down the middle, we'd be able to see that a little bit better. I don't know if I can color on them. I can't. But if you were to split this kind of right in half, and this is one duct system, this is the other duct system, you can't have something that is so unevenly distributed. So if this side fails but this side passes, great. The system fails the new way it used to pass. And here's a look at it from the leakage outside. So same thing, same house, 1200 on one side, 16 on the other. You'd need 48 or better, or 64 and better, and same way with total leakage. The best way that I look at this is, if you think about the duct system as the air dancer, or crazy legs guy, whatever he's called, if you split him down the middle and he's got a system on each foot, they need to stand on their own. So each side needs to be adequately sealed. You can't have a separation of the system. So on to this 4.3, I thought it was important to keep this in because as it being recommended to seal duct boots to the floor while sealing using caulk foam, mastic tape, or mastic paste. Now, just some examples to run through this quickly. And here's an example of sealing the duct boot to the floor. Highly recommended. Lose significant, you can get significant gains on your duct sealing and tightness on the test out of the duct by making an effort to try to seal this down. And here's an example of a sealed section that's with the boot sealed into the drywall. So for the third and now final time, just want to mention again, the requirement that's changed for a home with a dedicated return in each bedroom, not a bedroom pressure balancing feature leading to a central return. The total rater measured duct leakage is permitted to be the following: the greater of 6 CFM per 100 square feet, or 60 CFM 25 at rough in, or the greater of the 12% at final. In regard to the certification process and ENERGY STAR, we always like to remind everyone that you can use the ENERGY STAR certification, as a sales tool, and that's what we've been trying to help with all along. Third-party testing and verification is very important in developing confidence for home buyers. There are checklists that are tangible pieces of evidence showing the comprehensive inspections that have been done to assure that it's a quality-built, durable, and healthy home. And don't forget about the marketing tools that are available for free from ENERGY STAR and through our FirstEnergy's New Homes program. To get access to the ENERGY STAR resources, just become a partner. You can order free marketing brochures from the website by accessing the My ENERGY STAR account, and access for co-brandable brochures, banners, and the ENERGY STAR consumer video. The ENERGY STAR marketing really helps to explain the benefits to clients. And if you haven't downloaded any of these pieces, it's again important to just know that there are detailed pieces that describe the complete thermal enclosure, complete heating and cooling systems, the water management system, efficient lighting and appliances, and of course independent inspections and testing is valuable in the construction of a new home. And don't forget about branding. Being an ENERGY STAR partner allows you to use the Energy Star brand and gain recognition that accompanies that logo for quality and energy savings. So make sure you take a moment to look at that. Normally this is where we'd be closing up, but I wanted to mention one more thing. That's the HVAC Energy Star credentialing. This process has become more streamlined. There are more resources available, and there's lower costs. If you want to look into both ACCA and Advanced Energy, the most recent information I've seen that for ACCA there's a $275 application fee, and then annually $800 for non-members and $600 a year for ACCA members. You can find more at their website, www.acca.org. And then Advanced Energy has streamlined some things as well. They now do everything online. They have a training exam fee of $300 with annual costs of $600 per year, and there's no additional fees for HVAC jobs that are submitted. I wasn't able to find that information for ACCA on my last check. So it's the Energy Efficient New Homes Program Review. You submit homes and you get paid. The builder incentive is, again, $400 per unit plus the 10 cents per kilowatt hour in projected savings. Eligibility is based on homes located in the service area of a FirstEnergy utility. A certificate of occupancy dates need to be in Ohio after March 23, 2011. For MedEd, Penelec, and Penn Power after October 28th of 2009, and for West Penn Power after June 1st of 2013. Homes need to be 15% more efficient than the 2009 IECC or relevant code when permitted, and need to be Energy Star certified. Keep in mind that as these incentives climb, it's based directly on the energy efficiency of the home and particularly the electric consumption. On average, an Energy Star home, gas heat will get an incentive of around $550. And if you're looking for ways to do two things, drive down your HERS index and get a better incentive from the program, you can look for support in addition to other energy efficiency standards such as the DOE Challenge Home, which is now the DOE Net Zero Energy Rating Home, I believe, and the Passive House standards. For some additional resources on codes, you can look at the International Code Council at publicecodes.cyberregs.com. There's the Energy Star website, a link to the DOE Challenge Home, which likely can be updated, Passive House, and of course, for very specific questions, always Building Science Corporation is a tremendous resource. So I want to thank everyone for tuning in today. I'm glad that we were able to get through that in a little less time than I thought, but appreciate everyone who was able to make it. Again, we'll get to any questions that we had via email, and be sure to catch the next installment here, which will be on November 13th for water-managed roofs and walls. Thanks for tuning in, everyone.